Now I want to take the population model that we just discussed, and we'll show you how to construct a model like this, given some information about a population. So in this particular problem, we're talking about the population of Metropolis, and according to a 2005 census, the population then was 13.8 million people. 5 years later, in 2010, the population had grown to 16.2 million. So assuming the population grows according to the model that we used in our first example, I want to construct the population model for the city of Metropolis and let t equal 0, let the initial time correspond to the year 2005. Well, in the model, the things you need to add to it are p sub 0, the value of k in the exponent, and that'll complete the model. Well, if t equals 0 is the initial timestamp, then that means the population in the year 2005, according to the census, is going to need to be our p sub 0 amount. So the actual p sub 0, the coefficient that goes right here, is given in the problem, since we're going to let 2005 correspond to the t equals 0 time. So we got one bit of data for free. So we can go ahead and refine our model to where it looks like this. P of t equals 13.8. And again, that means you'll need to pronounce the word millions. The actual units for this model will be in millions of people. So we're just abbreviating it using the 13.8, but just keep in mind that the scale is going to be in millions of people. Okay, so we've got one of our two unknowns that we need for the formula. You know, e is obviously a constant; it has a designated value, and t is the independent variable. So you'll need to leave t in the formula when we finally get the model built. Now we just need to determine the value of k. Well, to get the k value, you're going to need to know a data point of the population. That's where the second sentence comes in. In year 2010, the population had grown to 16.2 million. So, in 2010, population equals 16.2 million. Well, you need to go ahead and correspond that to a value of t. If t equals 0 corresponds to the year 2005, then that means 2010 corresponds to the year t equals 5. So in terms of function notation, we want to be able to plug 5 into this function and get an output of 16.2 million. Okay, so if I take the model that I've got so far and I plug in the value 5, p of 5 will equal 13.8 e to the k times 5, because you're plugging in 5 for the year time. So this will help us figure out the value of k, because we know we want to force this to equal 16.2 million for the population in the year 2010. So this right here is the exponential equation you'll have to solve in order to determine the k value that represents the relative growth rate of the Metropolis population. So the procedure in solving this, we would need to divide by 13.8. Yeah, it's an exponential equation, so you want to get that e by itself. So that says e to the 5 times k equals 16.2 over 13.8. And now we want to get the variable out of the exponent, so this is when we'll use the cancellation properties. Take the natural log of the left-hand side, take the natural log of the right-hand side, so you can use those cancellation properties, and then that will free up the exponent. 5k will equal the natural log of 16.2 over 13.8. So we finally divide by 5, and this represents the calculator entry that you need to do to figure out your k value. And divide that natural log by 5. So let's go to the calculator and crunch out our k value. So according to this, I need the natural log of 16.2 divided by 13.8. Close off the logs argument, because now you need to divide the entire logarithm by 5. Divided by 5. So this represents an approximation of our k value. Now, a good idea is to use maybe 4 or 5 digits for k. So I'm going to go in and round it to 5 digits after the decimal. That's about 0.03207. Because that 6th digit is an 8. So yeah, that would round to 0.03207. And then, now that we know K, we can complete our final model. Our population model is going to be P of T equals, go back to here, this is what it started off looking like, 13.8 times e to the kt, and now use your approximation of k, and that again is scaled in millions of people. For the units. So now we've got a pretty reliable model that can help us do predictions about the population of Metropolis for times that are pretty close to this time period. Okay, so using this model, let's go ahead and estimate what the population would have been in the year 2012. So the year 2012, keep in mind your t-value needs to correspond to the time it's been since 2005. T equals 0 is 2005. T equals 5 was 2010. So therefore, 2012 will correspond to T equals 7. So in this case, I just want to use the model we just built and evaluate it with an input of 7. So P of 7 will be 13.8 times E to the 0.03207 times 7. And that's all tucked in the exponent. And so let's see what that's approximately going to be. So let's see. 13.8 times e raised to the 0.03207 times 7. And again, that's all inside the exponent. You may have to use parentheses if you're using an older operating system than this. But that's going to give me approximately 17.3. Since the population so far has been rounded to the nearest tenth of a million, I'll go ahead and say that's about 17.3 million people. 17.3 million would have been roughly the population of Metropolis in the year 2012. Okay, so now let's use the model in a different way. Whenever you're given a particular time, all you need to do is turn the time into the t-value, plug it into the model, and that gives you a future population. Well, if you know a future population, like in this example C, you've got to be able to use the model to figure out the time that corresponds to it. According to the model, how long will it take the population to grow to 20 million people? Well, it took 7 years after 2005 to get to 17.3, so I know this should be a year bigger than 2012. So let's figure it out. This corresponds to a future population value. So that's what you're going to replace P of T with in the actual model itself. And see, that'll generate a exponential equation to solve. So the future population is 20 million, and I want to force that to equal my model equation, or my model formula. And it creates an exponential equation to solve, similar to the one we solved earlier for K, but now we're just solving for T to get the time it takes for the population to grow to that amount. So exponential equation, get the E by itself, divide that 13.8 across, oops, 207, and then I want to get the variable out of the exponent, so this is when I need to use the natural log cancellation property for exponential base E. Cancels out. So I'll have natural log of 20 over 13.8 equals 0.03207 times t. So here's the calculation I need to do in my calculator. T will equal the natural log of 20 over 13.8 divided by my k value, 0.03207, and let's see what time that's going to produce. So ln of 20 over 13.8 divide that by 0.03207, and that'll approximately be 11.6 years later. And again, remember, that's years after 2005. So you could also say, you know, a little over 11 years after 2005, that'd be somewhere around 2016. Would have been when the population grew to 20 million people. Okay? So that's another example of the kind of problem that you'll have to do with populations, is actually build the model itself, given a few bits of data about the population.